So shall we start? Are we okay?
We are ready to go, John.
That's great. All right. So good morning, everyone. Good morning here in Turkey and good evening in New Zealand. My name is Mauricio Morales Beltran. On behalf of the Department of Architecture, I give you a very warm welcome to our Earthquake and Buildings panel. The goal of this panel is to raise awareness among the architects, among us, of our role in the seismic performance of buildings. So for that reason, to accomplish that goal, we have today two very distinguished guests who are going to take us in this let's say journey into the relationship between buildings and seismic design. In the first presentation from Professor Mehmet Nuray Aydinoğlu, he will show us the effects of the earthquake in the last earthquake in Izmir on the buildings in Bayrakli here. And then after that presentation, Professor Andrew Charson from New Zealand will show us the relationship between seismic design and architecture. So after those two presentations, we will have a conversation about this idea of the architects in their role in the seismic design of building. What is our role? And at that time, questions about these or comments are very much welcome from the audience. I would like to introduce properly my guest, not just by the name. I would like to shortly introduce all of you, our very distinguished guests. I will start by Professor Dr. Mehmet Nuray Aydinoğlu. He graduated from Istanbul Technical University in 1965, started his career as a structural design engineer shortly. He received his PhD in 1977 and associate professorship in 1981, and working in Institute Technology, Izmir, Istanbul Technical University. And he worked as a practical engineer in the construction industry until 1992. He joined Kandili Observatory and the Earthquake Research Institute in 1992, and he continued working in the Department of Earthquake Engineering until officially he retired in 2010. He still continued performing some activities at Coeri Institute as emeritus professor. His research interests include seismic soil structure interaction, performance-based seismic analysis and design of buildings, and other civil engineering structures. He's actively involved in engineering industry as a structural earthquake engineering consultant and served in several governmental councils and committees. We are very much pleased to meet Professor Aydinoğlu. Thank you very much for joining us. I would like to introduce also Professor Andrew Charson. Andrew Charson recently retired as an associate professor from the School of Architecture, Victoria University of Wellington, New Zealand. He has taught the subject of architectural structures in studio settings for over 30 years. Prior to that, he worked as a structural engineer. Professor Charson has two main strands of research interests. The first strand, how structure can enrich architecture, was brought together in the book Structure as Architecture, a source book for architects and structural engineers, which was published in 2005, and a second edition was published in 2014. The second research strand related to earthquake engineering. Professor Charson is the former director of the Earthquake Hazard Center an NGO that disseminates earthquake damage mitigation information to developing countries. In 2008, his book, Seismic Design for Architects, How Within the Quake, was published by Elsevier, and he's the co-author of Seismic Isolation for Architect, published in 2016. We are, our Department of Architecture is delighted to have such a distinguished guest. Thank you very much, both of you, for being here. And now I will leave the stage to Professor Aydinoğlu for his presentation. Professor, please.
Thank you very much, Dr. Beltran. Thank you very much for inviting me to this important meeting. And I'd like to congratulate you and your department for organizing in such a rather rarely organized meetings with engineers, combining engineers and architects. The collaboration between these two branches of construction industry has always been a problem for in Turkey, especially because we still struggle to find a common language between engineers and architects on seismic design issues, especially, which is the vital, which has a vital importance in Turkey, you know. So I'm very happy that you organized such a meeting, and I accepted it with pleasure, just to contribute a bit to the architectural students and architects as audience of this webinar. So, as you asked me to talk about the latest earthquake, recent earthquake in Izmir area, so I will present a few slides about the damage occurred during the earthquake and some earthquake engineering aspects of the earthquake. And finally, I will talk about the outcome of the earthquake in terms of damage and the reasons of damage and the lessons we have to draw from this experience. Now, the earthquake occurred actually in Samos Islands, southwest of Izmir, and the epicenter is about 70 kilometers away from the central Izmir area, or the Bayraklı area, where we had the damage concentrated mainly in the earthquake. Well, it was not a small earthquake. The magnitude of the earthquake was measured as 7 moment magnitude. It's not a small earthquake. It's an important earthquake. But considering the distance to Izmir, of course, normally you shouldn't expect such a damage. But away from 70 kilometers away from the epicenter, we experienced considerable damage in the particular region of the city, namely Bayraklı region. As you see in this map, well, some damage also occurred in other parts. For example, in Karşıyaka, mainly, which is not far from, actually, from Bayraklı region, but the damage was concentrated, or heavy damage, actually speaking, was concentrated in Bayraklı area. I know this area for some time, at least in the last 10 years, because as I will be talking about towards the end of the presentation, this area, incidentally, has been allocated to tall buildings. And since 2011, approximately, within the last 10 years, there have been some tall building development there, and I have been involved especially in developing the design guidelines for those buildings to be built on rather adverse soil conditions. Now, the soil conditions there is quite important because Bayrakli area is a basin, actually, which is called Bornova Basin, actually. So it's a deep sedimentary material, very deep, hundreds of meters deep, historically or geologically developed in various stages. But of course, we have very adverse conditions in terms of seismic response. Now, this slide shows Bayrakli area at the center, and the Manavkuyu region is the region or the district where the damage is concentrated. Now, the soil conditions, as I said, are very weak, and the shear wave velocities are very low in the area. Now, here we have a pseudo-acceleration spectra of the earthquake based on the acceleration record recorded at this station here, station number 3513, near the shore. The soil conditions are very weak there, and the shear wave velocity is estimated around 200 meters per second. There are several, actually, earthquake records, thanks to AFAD agency of Turkey, because they have installed numerous strong ground motion stations, accelerographs, and so we have plenty of them. Now I will show you here the results of just 3 of them. The one is 3513 is on the shore on the left, is on the weak soil, but the other 2, 3514 and 3520, these stations are located towards the end of the basin. So towards the outskirts of the hilly areas surrounding the basin, okay, to the north. And in these areas, the soil conditions are very good. These are rocky sites with shear wave velocities are in excess of 800 meters per second. So practically we treat them as rock in engineering. Now, here you see 2 response spectra. So maybe I should say a few words. What does response spectrum means? So architects may not be familiar with them. Actually, this is a simple graph showing the level of seismic load to be acting on our structures in a given location. In the horizontal axis, you see the natural period of structure, and in vertical axis, you see in normalized form in terms of g, acceleration of gravity, the total accelerations to be experienced on a generic typical structure. So these graphs are key elements for us in seismic design, in determining and in specifying the level of earthquake forces acting on our structures. So on the left, there are three response spectra you see here in the upper part with solid lines are the ones measured. This spectra is based on the recording at 3513 on weak soil. And the other two, as you see from both figures, with dotted lines, they are from other locations, rocky sites. You can see an appreciable amplification of accelerations due to soil effect. This is what we call soil amplification. This is an already known phenomena, and we have seen here an actual example of it very drastically. So as you can see from these figures, by the way, on the left-hand side, we see the response spectra obtained from the record measured at east-west direction, and on the right, from the record on north-south direction. So the level of amplification is around 4 or 5, within the range of, say, 0.3 seconds up to 1.5 seconds or so. So it means that if the effect of earthquake will be increased approximately 4 to 5 times with respect to rocky sites in the on the weak soil conditions at Bayraklı area. Now, in engineering, seismic engineering, and in seismic codes all over the world, this is a very well-known effect. So the effect of soil is definitely considered in specifying the level of earthquake forces to be acting on the structures. So it is the case for Turkish codes. Now I will show you a slide. Here we have two stations on the left. Bayraklı station, again, the same station, 3513. And the other is on the right, Karşıyaka station, 3519. In Karşıyaka, we had also some damage, but fortunately, no collapses. But in some buildings, although not very much, talked about in the press or in the media, but there have been some damage there, inside the buildings. We know that those. So actually, the soil conditions in Karşıyaka station is even worse than Bayraklı station. As you see here, the shear wave velocity at that location is estimated as around 130 meters per second, a very, very weak soil. And of course, the Karşıyaka area and in the vicinity, Bayraklı, Mavişehir area and Bostanlı area do have also very weak soil conditions. Now, in these two figures on the left and right, at the top you see the east-west and north-south records of the actually recorded earthquake. Well, the peak ground accelerations, as indicated on the sides, are not very high, approximately 10% of G. Well, in Karşıyaka, okay, a little bit higher. The north-south component has approximately 15% of G. But these are not very high, actually, peak ground accelerations. These are expected. But because, the response spectra ordinates, for flexible buildings are amplified. And in those periods, for flexible buildings or moderately flexible buildings, well, I'm talking about the buildings that have already damaged and even collapsed. So say the buildings up to 8-9 stories, which might have a natural period of around 1 second or even something less maybe, depending on the structural system. Now, the graph on the left-hand side shows the response spectra, which I already showed in the previous slide, for the north-south and east-west directions in the bottom part of the graph, of the figure. And in the upper part, these are the response spectra specified in various versions of our seismic design code. Now, these buildings which have had, considerable damage and even collapses, it has been reported that these buildings have been constructed between 1990 and 2000. So, okay. And at that time, the Turkish seismic code was the one that dated 1975. And later on, the code was modified in 1997 and published in 1998, just before the disastrous Adapazarı and Izmit earthquakes. And then a modification and revision has been made in 2007. And finally, our new code has been published in 2018 and has been put into force in 1st of January of 2019, almost 2 years ago. Now, in all of these codes, of course, the soil effect has been considered. Now, you see in the green line shows the recent spectra based on 2019 code. Actually, these data are provided not in the code, but the main data are provided in the seismic hazard maps. Incidentally, the latest Turkish seismic hazard map, or maps I should say, has been published in the same day with the new code in 2018. And it is a modern map, based on probabilistic investigation of the earthquake hazard in Turkey, throughout Turkey. And it's a modern map. So, the red line here shows the response spectra specified in 2007 code, and it was the same actually with the previous code, 1998. So it looks like a lower bit in short periods, but higher in flexible buildings going to the right. And the lowest, purple and brown lines shows 1975 code response spectra. There are three spectra you see there because, in 75 code, the spectral values have been given considering the type of buildings, So they were inverted as an elastic spectra, as we call it, by assuming various types of building typologies. It's not important to go into detail at this moment. So of course they are a little bit smaller than the other two codes, but still both are exceeding the actually recorded accelerations, okay? So, categorically we can say that those structures, collapsed structures or heavily damaged structures, shouldn't have an important damage because the earthquake demand specified in the earthquake, are higher than the actually measured accelerations. But of course, as we will see, we will discuss towards the end at the end of this presentation, we have many deficiencies in our construction practice, unfortunately, and it is clear that the capacity, the seismic capacity, seismic resistance of our buildings were not sufficient enough to cope with the code-specified earthquake effects. The problem is, of course, mainly coming from the construction practice. But I should say also, the design practice since 1975 has improved tremendously in earthquake engineering. And so our codes have been tremendously developed, compared to previous code, 2007 code was about, just to give an idea about the scope, our previous code, 2007 code was about 200 pages. Now the new code, 2019 or 18 code, whatever, is 400 pages. So, and because of the development in our knowledge, in the nature and the effect of earthquakes on our structures, but we have very important problems in design aspects, design part of the problem. And of course, in 1975 codes and in the conditions before 2000, the design, the understanding of the code requirements by the engineers were lacking, we were deficient. In addition to our so many problems with the concrete quality or material quality and workmanship quality and so forth. So basically, what I'm trying to say that, okay, on the paper, it looks like that those buildings shouldn't have damaged or at least shouldn't have collapsed. Maybe they might have some minor damage, but we experience terrible behavior and and many buildings were collapsed. 6 of buildings are totally collapsed, and several buildings are partially collapsed in first-story collapses mainly, or few lower-story collapses. Now, I will show you some examples of those terrible scenes. These are 2 photographs taken from totally collapsed buildings. There are, as far as we know, 6 totally buildings collapsed. And of course, unfortunately, we had many casualties in these buildings, and many injured people. And these are some, examples, damage details of the totally collapsed buildings. Well, majority of the buildings, I'm sorry, not majority, but a number of buildings, I should say, have experienced, interestingly, one first-story or first few story, lower story collapses. We can call it partial collapse, okay? So for example, you can see here 2 identical buildings. Actually, both of them have first-story collapse, okay? Now, why they have collapsed in their first story, we will talk about later. This example is very interesting. This is, I think, the name of this buildings was Barış Sitesi or Barış Building Complex. There were 4 buildings of identical size and identical construction, identical planning, and etc. And 3 of them had lower story collapses, first story or few lower stories, first and second, for example. At the center, you see, I think, 2-story collapse in the lower 2 stories. But interestingly, this 4th building, identical building, didn't collapse. Well, it had some few cracks, infill wall cracks looking from outside. There must be some cracks, wall or local damage actually inside, but at least we see that contrary to other 3 identical buildings, these 4th buildings are standing still. So it's quite interesting. Why is that? So this has been a discussion. I don't know, maybe still they are discussing, the local engineers and the academicians in Izmir are maybe they will come up with some conclusions. But as of today, I know some possible explanations based on certain considerations, but well, maybe further investigations will shed light into the real nature of the, because there are several rumors I will discuss at the end of the presentation. Again, there are 2 identical buildings. One on the left collapsed, lower few stories collapsed, and the right didn't collapse. There are several buildings, which is indicated in the very nice report prepared by Izmir 9 Eylül University right after the earthquake. There are several buildings of the same height or the same type, and built in the same conditions practically by the same type of contractors, and so they didn't have any appreciable damage. Okay, they might have some, wall cracks, infill wall cracks, or here or there some, local damages, but it is normal. Okay, it's not a simple earthquake. Of course, we might have some damage. But the problem here is the collapses and total failure of structures. So you see here, these are buildings that have been almost intact. And these are some other examples. There are some cracks you see on the walls, but these are infill walls. These are not structural cracks, so they are not critical in terms of seismic safety. Well, and here you see some local damages, okay, in the structural elements. I just have chosen just 3 of them, which are typical. On the left, you see a shear crack on a beam. It's a very typical 45 degrees, okay, because the shear stresses, occur in an inclined fashion. So we have concrete cracks. Apparently, there are not enough reinforcement, transverse reinforcement to avoid the formation of some cracks. This is our, of course, main problems, the transverse reinforcement in beams and columns, which have 2 major roles in seismic response. One is that they confine the cross-section columns and they confine the central core of concrete, okay? And the second thing, they act against the shear action. Apparently, this beam has been damaged due to most probably lack of transverse reinforcement. At the center, you see a typical column damage at the top. You see the rebars at the top have buckled. Apparently, we don't notice almost no stirrups or no transverse reinforcement. This is a very typical damage pattern due to mainly lack of transverse reinforcement. I should say that, the people at the first glance may not appreciate the importance of lateral or transverse reinforcement. These are stirrups, as you know, or spirals in circular columns. These have vital importance because we need them to increase the deformation capacity of concrete. The deformation capacity of the concrete is actually very low, okay? The concrete itself is not a ductile element. We make it ductile utilizing the transverse reinforcement, okay? So by those transverse reinforcement, we increase the deformation capacity of axial deformations in concrete. So on the right, you have a typical example of a short column failure. Apparently, this short column may not be an actual short column, but it may happen to be a short column due to failure of a nearby brick walls, infill wall. Okay, so when this part of the brick wall, damaged and lost its strength, then this column has become a short column here, where in this short column we experience a very high shear forces. And of course, again, the reinforcement inside is not adequate to cope with those high shear forces. Okay, now this slide shows Bayraklı area, okay, and you see here several tall buildings. There are, I don't know the exact number as of today. I think it exceeds 10 or 15. Actually, these tall building development started in 2011. At that time, there was no, design guidelines for for tall buildings because tall buildings have to be designed to special design guidelines, which are rather different than the regular or ordinary buildings. And actually, for example, in our recent code, in 2019 code, we have a special chapter devoted to tall buildings. They are designed according to what we call today performance-based design principles. And at that time, in 2011, there was an attempt to start the tall building construction in Izmir. And so we, Kandilli Observatory, we, Department of Earthquake Engineering, we helped Izmir Municipality and Izmir Chamber of Civil Engineers to develop those guidelines for tall building design, and including, very important, of course, because of the very weak soil conditions, as I mentioned at the beginning, of course, the foundations of those buildings has a very, very crucial role in response. So they have to be designed and built very carefully. And soil structure interaction, seismic soil structure interaction phenomenon, which is quite important here. So in those guidelines, we have also developed some practical methods to consider the soil structure interaction in design and construction of those buildings. I'm very happy to see that almost no damage has been observed in tall buildings in Bayraklı, just at the heart of the earthquake damage, okay? So, because they were constructed based on strict construction supervision, and the designs were made, experienced engineers in Turkey in this field. And as I mentioned, the new code actually covers, and the new code also has brought a new peer design peer review mechanism in which the designs are continuously reviewed by specially selected experts by the ministry. So we can say that the quality of those buildings had been good, and it is proven during the last earthquake. Now, I will talk now about some conclusions that we can draw from this experience in Izmir earthquake. So first of all, I'm reading from the text. All damaged and collapsed buildings in Bayraklı district are reported to be constructed in early 19th, according to 1975 seismic design code, as I mentioned. Well, and seismic coefficient or seismic accelerations given in 1975 codes appears to be sufficient, as I mentioned. But whether local site conditions as well as ductility classification had been properly considered are doubtful. Now, not only the earthquake effects are considered in the design of buildings or structures, we also consider the ductility capacity of our structure. So if we have enough ductility capacity, okay, and if we realize it in the construction, we are entitled to use a lower seismic effect. So seismic loads are actually decreased considering the ductility capacity of our structures. But the problem here, I clearly know from the practice of those days in 1975s and actually before 2000, ductility classification had not been properly made in the code itself, and the design engineers, unfortunately, didn't realize the importance of ductility property, which is crucial very crucial for the seismic design. Now, of course, the design quality must be very poor. We don't know the designs, actual designs, but it is inferred from the engineering practice known at that time. In particular, structural system arrangements, which is quite important, of course, for architects, and element dimensioning. For example, the columns are seen to be undersized generally. Reinforcement detailing were mostly deficient. Adequate confinement reinforcement or transverse reinforcement I previously mentioned in columns as well as in column beam joints, which is very crucial, were mostly lacking. These are very, very important details. Unfortunately, we observe these problems in almost all earthquakes in recent history. The main cause of the heavy damage should be attributed to the poor construction practice run by mostly incompetent contractors. The contracting is still a problem in Turkey, okay? In recent years, we have much better construction firms, but in generally, the construction industry has still huge problems in terms of quality, in terms of organization, in terms of expertise, and so forth. Of course, I'm not talking about the big contractors, experienced contractors, but the majority of the buildings, especially the buildings those collapsed in the earthquake, Izmir earthquake, must have been constructed by incompetent contractors. The workmanship quality was generally poor, as observed from the damage. Well, now it's interesting that there have been widespread discussions after the earthquake in public, as well as in engineering circles, on the possible causes of first-story and lower-story collapses occurred in many buildings, as I showed earlier. The rumors claiming that some first-story columns were cut and removed to provide open space for grocery stores and other shops, I think they were mostly unsubstantiated. They were mainly rumors. But an important effect regarding that is that a group of engineers and academia evaluates that removal of infill walls, not load-carrying walls, infill walls, these are brick walls mainly, for the same purpose, namely, in order to open space for stores and etc. shops. Though that may lead to reduction in story shear capacities and hence collapses. Now, this is important, and we face this problem almost in all earthquakes. The infill walls are not considered in Turkish code practice as seismic load-bearing elements because they are very weak generally, okay? They are infill walls. They are not intended to carry seismic loads. But in spite of their apparent weaknesses, they may still contribute to the story shear capacity in such a small earthquake without failure in view of insufficient shear capacities of the concrete elements. The problem is the relative strength of elements. Normally the wall capacities, wall strengths are very low. They are expected to crack at the beginning of earthquake and don't contribute to the response anymore. Because we are expecting that frame elements, namely columns, walls, and concrete walls, and beams, and etc. The frame elements will, work against the earthquake, and the infill wall damage is not important. They can damage, they can crack, no problem. But because of the weakness of those main concrete elements, reinforced concrete elements, relatively, the brick walls may have relatively higher strength than the columns. It's an abnormal situation, but that's the case. And well, the workmanship for the walls may vary. Okay, in some cases you might have a good master, okay, and he can make a good wall, strong wall, because it depends on workmanship and material, of course. So this is an abnormal situation, but apparently, since the columns were very weak in those collapsed buildings, some of them, of course, you know, and for example, in the Barish complex, I mentioned there were 4 buildings. One was intact. 3 of them collapsed, partially collapsed. And it is reported that in those 3 collapsed buildings, the first story walls, infill walls, were removed to open space. But in the 4th one, they were not removed. So apparently, or it is estimated that they worked and they saved the building. Well, they are not intended to do, but it might be the case. Well, it needs to be clarified by additional investigations. But on the other hand, there are other considerations. For example, it has been reported that the 4th building, undamaged building or uncollapsed building, had been constructed by another contractor. You see, so the concrete quality or other effects may play role. Now I'm showing here at the bottom a simple detail to separate the infill walls from structural elements. Okay, if they don't work together, okay, in the earthquake, that such adverse effects of walls will not affect the columns or walls and others. So what we propose here, this figure has been included in our recent code. Now we are separating by a simple detail, as you see here, to the sides of the column, we place a U-channel type of steel. This could be a cold form steel, and then we provide a gap, a reasonable gap, okay, based on the expected deformation of the story, relative deformation, and okay, you can practically isolate the wall from the column, and you can use an infill material in between. Okay, so the similar details we know are also applied in other countries. This is not mandatory, but it has been, included in our code as a precautionary situation in case. Now, of course, in recent construction, we generally use lighter wall materials and weaker wall materials. So this problem shouldn't occur in modern construction. Well, as a final words, it is unfortunate to conclude that we appear to continue to suffer such heavy damages in such a relatively small to medium intensity earthquakes. I mean, this is not a small earthquake, but in terms of its effect to Izmir, it's not a big earthquake. It's 70 kilometers away. Well, unless we develop sound engineering and construction practices supported by adequate quality control systems, we hope necessary lessons are drawn in time to be prepared for the expected Izmir earthquake. These are expected Izmir earthquake. What is it? this was not an Izmir earthquake. This was a Samos Island earthquake. We have a major Izmir fault crossing the city all throughout the main city center. So the main earthquake that would affect the city of Izmir will be due to this fault, which we might call, which it is called Izmir fault. And the real Izmir earthquake is still being expected. So finally, contrary to this heartbreaking scene, it is observed that a number of tall buildings built at Bayraklı area since 2011 performed very well as expected, thanks to advanced engineering and construction practices applied in adverse site conditions. So I hope I have finished in time. So thank you very much for your kind attention.
Thanks. Thank you very much to you, Professor Adinolu, for that very, very interesting presentation. Yes, you did it almost perfectly in time. So thank you very much. That's perfectly fine in the frame we have for that. As I said at the beginning, at the end of the Professor Charlson presentation, I will come back to you both to have a conversation, and we can retake some of these, the points you have made that deserve some more commenting. So thank you again, Professor Adinolu, for the presentation. And I would like now to give the stage to Professor Charlson. Andrew, if you can, Omar, Jan, maybe you can give Professor Charlson the possibility of uploading his or sharing his screen.
I think Professor Charlson is already has that permission.
Okay. All right. Okay, so it seems we are receiving your screen view. Yes. However, we cannot hear you, Andrew.
Now can you hear me?
Now it's perfectly clear.
Oh, lovely. Okay. Well, thank you very much for inviting me to give this presentation. I must say, I've really enjoyed hearing about the recent Izmir earthquake. Or sorry, it's not actually, it was the earthquake that occurred near Izmir. And some of what I say will, of course, relate to some of the slides we have just seen. So my presentation is very much geared towards architects and architectural students, because I'm talking about 7 key principles of architectural seismic design. And so I'd like to encourage the students who are participating to make a few notes so that you can use these principles as a checklist for your own studio design projects. And for practicing architects, these principles also could be used as a checklist for the work that you're doing in your architectural practice. So by way of introduction, you don't need me to tell you that you in Izmir are living in a very seismically active zone. You've just been told that one day there's going to be a significantly larger earthquake affecting Izmir when the fault lines running through your city, move. And so you're living in a very seismically active zone. And so during an earthquake, the ground will shake. And you as an architect have to assume that every design that you do is going to be subject to very strong, especially horizontal shaking. It's the horizontal shaking that causes most of our problems. And so when the ground moves to the left suddenly, it forces the development of earth inertia forces in the superstructure of the building. And these inertia forces are the forces that cause damage, damage columns and beams, and cause non-structural damage. And so the principles that I am about to give you are to enable your designs to withstand these inertia forces during an earthquake. Now, before I start the principles, I just want to mention 2 points. And this is that as the architect, I believe you should be conducting the preliminary structural design of your building, ideally in collaboration with a structural engineer, because it's your responsibility that the structure you provide is integrated with the building program. You know, it's no use having columns in the middle of lecture theatres. That is absurd. It is no use having columns in the middle of a cinema. And so your structure must integrate, well, beautifully with your program. And secondly, it's important for you to do the preliminary design in order that the structure of your building can enhance your design concept. For example, if you've got a design concept that's about transparency, you want a very transparent building, well then you definitely don't want structural walls or shear walls as your structural system. And so that's why you as the architect have to drive the preliminary design. Ideally, the engineer will be at your side to help you with this. And then when you've done the preliminary design, the engineer will go and do very detailed calculations and detailing. And so that's how I believe it should work. So let's start with the 7 principles. Principle number 1 is that as an architect, you've got to provide seismic resisting structure in plan in 2 directions at right angles. Let me explain. This is a plan view of a building, and we could imagine the building is situated at the intersection of the X and Y axes. And we don't know the angle of the earthquake attack. Now, actually, during an earthquake, the shaking comes from any and all directions. And so our buildings have to be strong against every direction of earthquake attack. And fortunately, it's fairly easy to do this. What we have to do is to provide strength in the X direction in plan and strength in the Y direction in plan. And if we do that, it means that if, for example, there's an earthquake attack at an angle to our axes, then that earthquake force can be resisted by the components of strength in the X direction and the Y direction. And so for every one of our designs in a seismic zone, we've got to have strength in 2 directions in plan. There are no exceptions. Principle number 2. Provide in each direction in plan a minimum of 2 lines of structure that are separated. And so here is an example of a simple, rather boring building, I must say, where forces in the y direction are resisted, in this case, by two structural walls. And in the x direction, the forces will be resisted by this wall and the wall above. The columns are relatively very slender and flexible, and so they won't resist much of the force. The forces will be resisted by the stiff and strong walls. And so this building, it satisfies principle 2, because in the y direction, there's a line of structure here and a line of structure here, and these two lines are separated by this horizontal distance. And the reason for the separation is that during an earthquake, buildings will twist in plan. They will experience torsion. And so we need to separate our lines of structure that resist the earthquake in the x and the y direction. Here's another building which satisfies that principle. In this building, in the x direction, the earthquake forces are resisted by two structural walls. See the structural wall here and a structural wall there. In the y direction, the earthquake forces are resisted by this framework of columns and beams. We call it a moment frame. It's got two bays, a two-bay frame here, and you can see there's another two-bay frame on the other side of the building. So these two frames, they are separated by the width of the building, and they're going to be very effective at resisting twisting in plan. I must say, this little building model on the right, it'll have lots of other columns to support the floor slabs, but the main structure to resist earthquake are the structural walls and these two moment frames. Principle 3. In each direction, that is like in the x direction and the y direction in plan, choose just one structural system out of 3 that rises from the foundations to the roof to resist seismic forces. So in each direction, you've got to choose one particular structural system, and it's got to start at the foundations and go right up to the roof. You can't interrupt it or cut it off. And so these are the 3 options we as architects and engineers have to resist earthquake forces in buildings. The best option is to use shear walls or structural walls, or we can use some type of a braced frame where we have triangulation, creating bracing. And finally, we can have what are called moment frames, which consists of columns and beams at each level. And so this principle says that in one direction, you should choose one of these systems. It's not advisable to mix them because they behave quite differently during an earthquake. And so in the X direction in your design, you might have 2 or 3 shear walls. And in the Y direction, you could have a number of moment frames in your building. Or if you wanted to, you could have moment frames in both directions. The choice is yours as the architect, You choose according to your program and your design concept. You don't choose to please the contractor. You choose because of program and concept. Principle number 4. You need to provide sufficiently large structure in each direction to resist seismic forces. It's no use having a multi-story building with tiny columns. It will collapse. As simple as that. And so you've got to design strong seismic structure for your building project. So how do you know how strong to make your structure? How do you know the size of your columns and beams and how many that you need? Well, here are 3 methods to help you. First of all, you can use a software program written for architects. It's free, and this very simple software enables you to work out the cross sections of your beams and columns and shear walls. It's very simple to use, and actually I think Mauricio will have a copy of the software, but in any event, you can download it free from that website. Now, if you don't use a software like that, the other option is for you to try and find a textbook which gives you typical sizes of columns and beams for different size buildings. And so you could use that information to guide you. For example, you may know of Francis Ching's textbook on building construction. Is it called Building Construction Illustrated or something like that? There he gives some very crude guidelines as to the size of the structure you need to resist earthquake. It's very crude, but it's better than nothing. And so you can use that. Or finally, you could look at precedents. You could look at some similar buildings in Izmir and look at the structure they are using and make sure that your building, has roughly equivalent sizes of columns and or lengths of shear walls. And so that's the third method you can use to make sure that you're not going to design a building with small columns and shallow beams or with skinny shear walls. Because if your structure is like that, then it will probably collapse in the next earthquake. Principle number 5 is to provide a structural diaphragm at the roof and at each floor level. Now, I just need to explain to you what a diaphragm is. A diaphragm has the role to tie the building together at each level so the building doesn't shake apart. And so at every level of your building, you need, I suppose, generally a strong floor slab that will tie everything together so everything will shake together and the building won't fall to pieces. And so that's the first role of a diaphragm, to tie everything together. The second role of a diaphragm, which is usually a floor slab, is to act as a horizontal beam. And so the role of the floor slab or the diaphragm is to transfer inertia forces to your seismic resisting structure, like shear walls or moment frames. Usually, almost always, in fact, floor and roof slabs, they can easily act as structural diaphragms. Maybe they might need a little bit of extra reinforcement, but often they don't because they are inherently strong. But if you don't have a roof slab on your building, maybe your structure is lightweight, then we normally would form a diaphragm by using cross bracing. And so in this particular roof, if we just look at forces in the y direction, to transfer forces in the y direction to bracing on the perimeter of the building, we require like these horizontal trusses. These are horizontal trusses. We call it a cross-braced diaphragm. And that has the role of resisting the forces in the y direction and transferring them to the bracing here and the bracing here. And in that way, these diaphragms are tying everything together and they're transferring all the forces to the safety of the cross-braced frames at each end. If we look at a typical story in a building during an earthquake, it looks like this. These are the inertia forces acting on the story. These are the inertia forces from the mass of the floor slab. These are the inertia forces from the column and maybe some infill walls or furniture or partitions. And so in section, every story has this type of inertia force diagram. And so this is a section through a moment frame building. Now, if we look at the same building in plan, here's the floor slab, and you can see all the inertia forces acting over every square meter of floor slab. And you can also see the inertia forces from the cladding here and here. This would be the inertia force from the cladding. And so the role of each floor slab or floor diaphragm is to resist all these forces and transfer them to each, in this case, each end of the building so that they can be resisted by the structural walls. And notice the way the floor diaphragm, it bends. Like that's the deflection in it. Like in a real building, that might be 20 to 50 millimeters deflection. And so it's crucial that the floor diaphragm, is strong enough to transfer these forces to get into the structural wall, and then the structural wall can transfer the forces down to the foundation. And then our building is going to be safe and strong. Now, when it comes to designing diaphragms, it brings us to the question of the architectural form of buildings. And as architects, your job, your responsibility is to avoid forms like these, because each of these forms have what we call re-entrant corners. Like that is a re-entrant corner. This building here has 4 re-entrant corners. This has 2, and this has 4. And the reason for avoiding re-entrant corners is because our diaphragms, they can't tie the building together because of its sort of weird and irregular form. It's impossible for the floor diaphragms to make this building all move as one unit in an earthquake. It's just not possible. And so what do we do as architects? We have to separate. And so if you have an L-shaped building like this, we as engineers would encourage you to design your building like this is one work of architecture, but it is two structures. And each of these structures are separated with a seismic separation gap. And so that during an earthquake, each of these buildings moves totally independently of the other. And then if we have a building with four reentrant corners, good architectural practice is to separate this form into three separate structures. Each structure can have a different structural system, actually. But here is a physical gap that depends, its width depends on the height of the building and the flexibility of the buildings. And the engineer will tell you how large that gap needs to be. You know, on a low-rise building, it might be 50 millimeters or 5 centimeters. In a 20-story building, the gap could be 1 meter. The engineer will advise you. Now to principle 6. And this starts to link in, I think, very nicely with our first presentation today. Because principle 6 states that architects must avoid critical structural weaknesses, especially what we call soft stories. And I'm going to explain what I mean by that. But in the professor's slides, he showed a number of buildings in Izmir that collapsed because the lower stories were soft. And this type of collapse is very common in every country in the world. So Turkey is not alone in this problem. It's the major reason buildings collapse in earthquakes. And so it is indeed the most dangerous structural weakness that we can design, really. And it's caused, first of all, when columns are weaker than beams, or if one story of your building is more flexible or weaker than the floor above. Those are the two conditions that generally lead to soft stories. Now this is the dangerous situation. This is a soft story here where we've got weak columns and strong beams. And so the columns of this building A are weaker than the beams. And so the columns become the weak link. And so during an earthquake, all the damage occurs at the tops and the bottoms of the columns, usually at the first floor or the ground level. And ironically, the rest of the superstructure remains undamaged. But as you saw from those slides, because we get collapse at ground level, the whole building has to be demolished. There's no way of saving it. And so the safe method of design is to have strong columns with weaker beams. And that means in an earthquake, our columns remain pretty much undamaged. We always expect damage just at the base of the column. We can't actually prevent that. But we make sure that the earthquake energy is absorbed by damage at the ends of our beams. And so that means that the earthquake energy is absorbed by lots and lots of beams, but we protect our columns from damage. And that's the critical thing. Once we damage our column, the chances are that the building will collapse because the columns support the whole weight of the building. So it's about protecting our columns by making them stronger than the beams when we have moment frames. Now here are some other examples of soft story buildings. Here is an example in A where the ground floor of the building is open. But you'll notice that in the upper stories, we've got some infill walls and they will make the beams stronger. And so as soon as we start putting infill walls into a building, it's making that story a lot stronger than the story below. And so we can be pretty confident that in an earthquake, this building will have a soft story because these infills are making the superstructure above a lot stronger. And therefore, these stories won't get damaged, but this story will. Another cause of soft stories is when we have one story higher than the other. And so notice that like these three columns here are quite a lot higher than the columns above. And this is very popular for architects, especially if they're designing buildings like hotels, where you want to have a higher first story, you know, maybe for a foyer or a reception area. And so when you have one story that is higher than another, that makes these columns a lot more flexible and potentially weaker than the columns above. That will lead to a soft story here. And that is potentially very dangerous. And finally, another example of a soft story building is when we have missing columns. I mean, maybe the architect wants a large open space at this floor, maybe for a ballroom or reception area, shops, who knows? But what we have is that we've just got, in this direction, 2 columns at the front of the building, and above we have 3 columns. And so potentially, once again, this ground floor story is going to be soft and it will be severely damaged during an earthquake. Now, we've already seen examples from Izmir of buildings with a soft story. But I just want to emphasize to you that this condition occurs in every country. These 2 buildings actually are from India. And the building on the right has completely lost its ground floor. It's just crushed. And this other one here is pretty close to collapsing as well. Each each of these buildings has a soft story. Notice how the columns are leaning at this ground level here. These columns are a lot taller than the columns above. See how the canopy columns are sloping. And so this tells us that the earthquake damage has occurred in this story, and pretty much the rest of the building above is undamaged. But this building is ruined. It'll have to be demolished. Here are some buildings actually from San Francisco. And they have lost their ground floors. Like there's a car that has been crushed. And so these buildings have fallen one story because of the weakness at that ground level. Maybe the columns were too small there, maybe not enough shear walls. There could be a number of reasons. Here's another building from the United States where the columns at ground level are very badly damaged. So this is a soft story, but actually above that level, the columns are in reasonable condition, not too badly damaged. And I think one of the reasons for the damage in this building was because of infill walls above this story. This story had very few infill walls. Here the infill walls started, and so the upper stories were very strong compared to the ground floor level. And finally, in this building here, you can also see very severe damage to the ground floor columns. And so, you know, different buildings, but suffering from that same dangerous condition of a soft story. I'd just like to say that if you are designing a building where you require a high first floor, or you require hanging columns, then what you need to do is to provide perhaps shear walls in your building to resist the earthquake forces. And so your design philosophy will be to have enough shear walls in your buildings in both directions to resist the earthquake. And then you can have these columns like this because their job is only to resist the gravity loads of your building. And so what it will mean is that your building will have this form, but within the plan of your building, you will have sets of shear walls in both directions to resist the earthquake forces. And that's how we do it when we have apparently soft stories. Okay. And so this is the last principle. But it's a pretty tricky and difficult principle. And so it's this, that you as architects, you've got to design and detail masonry infill walls, first to prevent injuries to people, and secondly, to avoid damage to the primary structure of your building. So let me explain. When engineers design buildings, they normally assume that if they are designing buildings using moment frames to resist earthquake, like columns and beams, like this bare moment frame here, they assume that these frames are open or bare, like there are no infill walls. And so they assume that during an earthquake, the columns can bend like this, and the beams can bend like this in a very attractive, gentle curves. But if an architect comes along and puts an infill between columns and beams, the frame cannot bend like a bare frame. And what happens is that as the frame experiences the inertia forces, the earthquake forces, the frame will try and move to the right, but it's partially prevented by the strength of the masonry infills. And so what happens is that the masonry infills, they form compression struts, like diagonal struts, like this and like that. And at the same time, because this diagonal of the frame, it gets longer, it causes a tension crack like that. And so during the earthquake, we get these large compression struts forming in this direction, and parallel with them, we get the cracks. And of course, during the earthquake, we get the same thing happening on the opposite diagonal. And so we get like X-shaped cracks. But one of the main problems with these compression forces is that they cause damage to the main structure. And we've already seen a slide where these compression forces caused a short column effect in a structural column in Izmir. And throughout the world, we see many occasions where, like, here's an infill wall here. See the way it's damaged the top of that column? It's pretty much blown out all the concrete there. And you can see the way the infill walls have collapsed and fallen out of the building, probably causing a lot of injury to passers-by. And here's another building here with lots of infill walls. And if you look carefully, you can see the damage to the tops of the columns, and sometimes to the bottoms of the columns as well. Look at the damage there. And you can see the sort of the 45, the diagonal crack, vaguely appearing through the infills. And so masonry infills, as we've already been told, are relatively stiff and strong. And so that means they're really incompatible with flexible columns and beams of moment frames. Here's another building that suffered damage to the tops of the columns caused by infills. Look at all these columns here. The tops of the columns have just been destroyed, and the infill masonry that has actually collapsed and has fallen onto the floor of this building. So, infills are so dangerous for people, and they're dangerous to the main structure because they damage the main structure and can lead to collapse. They can also lead to soft stories. Like, imagine this is an elevation or section through a building. We've got a moment frame going up here, columns and beams. And at the upper floors, we've got infills. And so the infills make these upper stories very strong compared to this story. So this story is so soft. It's going to be the weak link during an earthquake, and most likely, you know, the building will collapse. Sometimes a soft story can occur in the mid-height of a building. Like in this building in India, you can see how this floor has collapsed totally. And maybe there were no infill walls at this level. I mean, I don't know the reason for the collapse, but it just shows that we've got to be very careful that we're not introducing, you know, or creating a soft story problem in one of our designs. It's also possible that these infill walls can create problems just when they're partial height. See, like here's an infill wall here, but it only goes to this height. It doesn't go to the full story height. And so effectively the infill prevents the lower part of the column from bending. We call this a captive column. And it means that all the earthquake energy is dissipated in this short length of column here. And usually such columns are far too weak to resist the earthquake forces. And the effect is, we call this a short column effect, which is another critical structural weakness that we as architects have to avoid. Here's another short column, this time from Japan. Here's the infill wall. The column can't bend up to this height, and above it's relatively short and brittle, and it just snaps with 45-degree cracks. Shear failure. So what are some of the solutions to preventing masonry infill walls causing such problems? The main solution has already been provided for us by Professor Aidan Low by using a concept of separation. And so he showed you the sketch from the Turkish seismic code. And basically this is the idea that if you've got an infill wall, you provide a physical gap between the edges of the wall and the columns so that the frame can move and it is not affected by the infill wall, which does not move because it's so stiff and strong. And so you have to discuss with your engineer what size of gap this needs to be. How wide does it need to be? The width depends on the flexibility of your building. If you want a very small gap, then you might have to ask your engineer to make your building stiffer. Perhaps use shear walls instead of moment frames. Now, of course, once we separate a wall from the frame, the wall becomes very unstable. And like this wall here, it could easily collapse like that. And so we've got to provide structure to prevent that collapse. And so one solution is to provide little columns in the infill that prevent the infill wall from collapsing. but yet allow for movement between the frame and the infill. And here's a little detail here where we allow the bars from these columns to move and flex, and thereby protect the infill from collapsing. And what are the other solutions? Well, there are a few other solutions. Probably the most popular solution these days is to avoid masonry infill walls and build your walls out of lightweight materials, like cement board or other systems of cladding. So using lightweight wall materials is one solution, because they are usually quite weak, and they will never damage your primary structure. Otherwise, if you're going to use masonry walls, well, don't build them in line with the columns. If you can build your walls outside the column line, then the columns are not going to be affected by those infills. And for low rise construction, if you're building in 1 or 2 stories, especially house construction, then I would recommend that you don't use infills, but you use a different construction technology called confined masonry construction. Okay, confined masonry construction. And you can Google that, and you can see that the principles of that construction technology use the masonry as a structural element, and that masonry is confined with small reinforced concrete columns and beams, and therefore they confine the masonry and make it safe. So for low-rise construction, that is a very, very good method or technology to use in your designs, confined masonry. And so there we are, 7 principles, and I do hope you'll use them as a checklist for all your design projects. That's all I'm going to say now, and I believe shortly the opportunity for questions and comments. Thank you very much.
Thank you, Andrew, for that very insightful presentation as well. I would propose you, Andrew, and to have a conversation about these subjects and open the session as well for questions and comments from the audience while we are talking about this. So perhaps we can lead them in a better way. Is it okay for you if we do it in that way?
Oh, yeah, sure. Okay, so the first question is, what's the role of architects and architectural design inside performance?
Yes, I want to have a conversation with you and Professor Adinolu about the role of the architects in seismic design, but given the let's say the subjects and the information you both have provided today in the previous presentations, I think that it would be better if we try to address this discussion or conversation with an example. So in both presentations, the issue of the soft story and the solution or partial solution to it related to the separation of walls was addressed. But for example, I would like to start this conversation by asking Professor Aydinoğlu. Let's assume that the buildings did collapse due to this self-story problem. I know that there is ongoing research, there is ongoing forensic engineering to finally determine the real cause, the real reasons why this building collapsed. But let's assume that they collapsed because this lack of infill walls on the ground floor, in the ground floor. But the question is, to me, what could be done, architectural decisions to prevent this one? And let me put the question in a little bit more clear context. We know, or we are assuming that the quality of the construction was poor, that there was a lack of transverse reinforcement. But for example, what if we'd have had designed these buildings with more shear walls? This is what I'm trying to go. What if we would have taken design decisions that might have given opportunity to the building to resist larger forces? Because in my opinion, the use of frames in the context of these poor building construction might have led to the collapse of the buildings. So I'm talking about design decisions, architectural design decisions, and let's say providing a little bit more of opportunities for these buildings to resist in this scenario. So what do you think?
So if I didn't misunderstood, you are saying, okay, to provide more strength to the structure to, to avoid the collapse, or maybe I misunderstood.
More or less, what I am saying is that you clearly explain that by removing, I mean, the hypothesis here is that if we, because removing the infill walls from the ground floor, then the columns remain very weak, not able to resist these lateral forces. But what if we would have had shear walls in the building? So what if the architectural decisions previous to the design would have been different? What could the architects have done different than these buildings? Okay. Shall we change the typology? Shall we use different materials? That is my question in a hypothetical scenario.
Okay. Well, as Professor Charleson already pointed out, the solutions that could be adopted to avoid the soft or weak story. I prefer to use the term weak story in order to express the strength. Soft story to me is rather related to the stiffness, but the strength-wise weak story. And we make this differentiation in our seismic code. Anyway, of course, there are, obvious solutions. The first one is to provide enough number of shear walls, okay? Now, for example, our new code requires the use of shear walls, almost not mandatory always, but, the requirements of the code leads you somehow to use at least some number of shear walls, especially in the new code. This is, of course, the most obvious solution. The second one, which is actually in new construction is already, happening in Turkey, is to use lightweight material, as again, Professor Charleson pointed out. For example, in Turkey, the use of gypsum board walls are becoming common. Actually, when I moved to my house that I recently live in, I demolished all the walls and replaced them with the gypsum walls. You know, so these are very efficient, and in Turkey I see them as the best solution. If not gypsum, there are some other materials. So this separation of walls, as we already I mentioned, the application in Turkish code, and also Professor Charlison mentioned, well, can be used, but of course may not be so practical and easy to apply in all conditions. It has to, the best way is to provide as much as more shear walls. But as I mentioned, that our new seismic code already forces the designer to use shear walls. For example, there are even low-rise buildings, 5, 6 stories, and so forth. In Turkey, it is mandatory to use elevators even for low-rise structures now. So around the elevators and stairs, it's obviously you can make a core wall, which would provide a good stiffness and strength for the structure. This is an normal application coming from these basic requirements. So well, of course, quality, concrete quality, and steel quality, and detailing quality, engineering quality. Well, basically these materials, even the masonry materials, because these in masonry walls, they are using blockwork blocks which are with a lot of voids in it, so they are not very strong elements actually, and the other materials to make the wall. If you want to make an infill wall, not a load-carrying wall, of course, the workmanship, the quality in terms of strength is not necessary. So actually, they are not built as strong as before. In older construction, the constructors, were making walls more strong. Nowadays, they are getting lighter and weaker. But still, it depends on the interaction between the, frame, columns, and beams and walls. So their relative strength plays an important role, as I mentioned. Yes.
I see. Thank you very much for your comments. I'm going to give the stage now to Professor Charlson to comment on these questions. Of course, Andrew, your presentation was much more on the core of the role of the architects and seismic design of buildings. And I would say mostly addressing the decisions we have to make from the early stages of the design in relationship with new buildings. Now, in that regard, I of course have read your book, Seismic Design for Architects, and in there you address the issue of the separation of walls that in a way that is possible to make the separation in an architectural way. That means that taking this gap not only from as a technical as a response to the need of separating the infill from the structural element, but also it gives the possibility for giving new, as a response. To elaborate a little bit on that regard.
Well, quite difficult to elaborate without me being able to show you some examples. I mean, I could use the screen to do some sketching, but I mean, I think the solution going into the future in Turkey is what we've heard is for architects to make more use of shear walls, and that means that if infills damage columns, it doesn't matter so much because the earthquake forces are not being resisted by the columns. They're primarily resisted by these shear walls. But I'd just like to give a word of warning about these shear walls. Often they have to be longer than the walls around an elevator. I mean, it depends on the height of your building. But if you have, say, a 10-story building, you've got to make sure that your shear walls are not too skinny in elevation, because then they will be too flexible and probably too weak. And so it's important for architects to realize that shear walls sometimes need to be quite long to be effective. And if you've got shear walls in a building, that means that the building is not going to move too much, and therefore you're not going to get a lot of damage probably with your infill materials, and you may not even need to separate your infills. And that would be a really good solution for practice, for engineers, contractor, and the building owner. So I think that's all I'd like to say at this stage.
I think what you are addressing to these adding shear walls and maybe maintaining the infills in the upper floors might help to solve what I call the cultural reason behind the soft story problem. Because the soft story problem or weak story problem is, let's say, comes from an architectural decision, or maybe from a decision taken by the occupants in the sense that they might remove the infill walls. But that is in response to a program. It's something you mentioned in your presentation, in the sense that usually, especially in Turkey, but I'm sure also in India, even in some places you show pictures from, the reason why the ground floor, first floor, is lacking walls is because the program requires openness, requires to show the people there have a restaurant, so they want to attract clients, or they have a showcase, a showroom, so they want the people to see what they are selling. So sometimes I feel like from the engineering perspective, we tend to look at the buildings as objects that are going to be, they're going to perform, and we try to keep them, of course, we design them within a performance threshold that guarantees safety. But at the same time, sometimes we forget that people is going to use these buildings, and the building should feed this purpose. So thinking that, for example, we should keep the infill walls in the ground floor, no matter what, I think will contradict this idea of respecting the program or following the function of the building. So again, what you're suggesting, for example, both of you are suggesting to increase the number of shear walls inside the building, and given to that, those shear walls, the priority and the strength capacity or the lateral resistant capacity rather than the infill walls, might help to keep this typology of buildings more or less in the way they look. I would say that would be my let's say perspective. I don't know if you agree or disagree with me. I would like to hear from you.
Yeah, well, if I could just share a screen with you.
Yeah,
like
please.
use a whiteboard. I mean, say we've got a building in plan like that, and we've got our columns, say like this. At ground level, this is like the ground floor plan. And let's assume that above ground floor level, we've got infill walls. So we've got potentially a soft story building. Well, what we have to do, like this is the plan, this is the ground floor plan. What I would suggest is that, like here, we create a concrete shear wall, and there. And so in the Y direction, these two shear walls are designed to resist the earthquake attack. And that means that we can have the openness in this part of the building. And then we've got to think about in the X direction. So, you know, maybe in the X direction, we might have a shear wall here, but we must always have two lines of structure. And so we would definitely need, say, another shear wall here. So in earthquake country, like Turkey and New Zealand and everywhere else, it's impossible really to have a perfectly open Le Corbusier ground floor unless we have we make these columns, you know, absolutely massive columns. I mean, that is another option, to make the columns really quite massive and make them stronger, you know, than the stories above. I mean, that is a possibility. But what I've shown you here is a scenario where we could use shear walls that will avoid a soft story, but it compromises the openness of the ground floor. And so I think when we live in an earthquake country, we've got to have some compromises. They are inevitable.
I definitely agree. Professor Adinolu, if you would like to comment on this, or should I continue with the next subject?
I agree with Professor Charlison about what he said. So you can proceed with the other stuff. Okay.
Okay. So I will say now at this point that I think we all agree that the architects and the architectural design plays an important role in the seismic performance of buildings. We have seen the effects of not considering these design decisions and early in the designs, and we also saw a presentation on how we can introduce these principles, 7 key principles in architectural design. But let's go into the architectural curriculum. We are talking about students of architecture. So the question, Professor Adinolu, for you first is, we have probably, I know you have been working also in university, so you know that currently, I mean, at this time, we have a highly constrained curriculum. So we have to provide a lot of knowledge to the students in shorter and shorter time. So the question is, what subjects related to what we have seen today, what subjects would you suggest to incorporate as minimum contents in the architectural curriculum, and at which level? Shall we teach students about this in the first year? Shall we teach students when they are graduating architects? What will be just your suggestion, seeing, of course, from your experience and as an engineer?
honestly speaking, for a long time I've been teaching. Sorry.
Yes, we can hear you.
Okay. Honestly speaking, for a long time I'm teaching only in graduate classes in the institute, so master and PhD classes for civil engineers mainly. So I haven't been involved for a long time, except a short time in my early days of profession in Istanbul Technical University. I haven't been involved with the architectural department. But generally speaking, you are right, because, you know, the curriculum in all fields, not probably in agriculture, also civil engineering. You know, the time limited for a thorough education is getting shorter and shorter, and of course, you know, for example, in civil engineering, it's inevitable that, you know, specialty areas has to be selected for students. One of the options may be, you know, a specialty area for seismic design. Okay, at least you, maybe not all architects, but, you know, a certain number of architects will be specialized, especially in seismic design. This may not be, you know, a good solution, because, you know, all architects should have at least have an idea about it. But, you know, Professor Carlson's presentation today, and although I didn't thoroughly read his book, but I reviewed from the internet that it contains a really useful information for students and architects. So these can be, I don't know which year, second year, third year, I don't know the, you know, curriculum of the architectural education. But, you know, in my opinion, they can be incorporated in a one semester course easily, and probably not in very early stages, because, you know, the design issues should, you know, design experience of students should, you know, improve a certain degree. And the curriculum, you know, could easily follow what Professor Charleson, you know, included in his book, in a one semester book. I don't know how is he himself doing in New Zealand. It might be a good guidance for us.
I agree. So, Andrew, what is your opinion? At which level and how much of this context should we deliver into architectural schools?
Well, I've thought about this issue quite a lot, really. And in this table, I've got all the topics related to earthquake design that are of relevance to architects. But then I've suggested that that we should definitely be teaching a minimum amount of material. And I think this, like here, for example, are 4 lectures and tutorials on these topics. They could be in the second and third year of a program. But I personally think that the ideal amount of material to be taught to architectural students, the ideal amount consists of 10 lectures or 10 sessions. and at the absolute maximum, maybe 14. But like, for example, we'll take the topic of non-structural elements that we've talked about today, like infill walls. Well, I mean, if a program has got very limited time, then we wouldn't cover that material. We would just concentrate on the need for, vertical structure and horizontal structure. But ideally, we would want to talk about infill walls and the way they affect the structure. And like ideally, it would be great to teach the students about seismic isolation. But we have to be practical and realize that, we do have limited time. So I personally think that we should be talking about seismic design maybe a little bit in second year, but definitely in third year. And we should be asking the students to design their buildings in third and fourth and fifth year against earthquake. We should be able to see the earthquake structure on the plans of their building projects. So that's all I want to say there.
I think it's very, very clear. Thank you very much. So I would like to come to the last question, which is, we'll say maybe less, how to say it? Might lack some scholar background, this question, but I think it became very relevant, especially here in Izmir after the earthquake. And before I make the question to our guests, I would like to encourage the audience to share their questions here in the chat. So maybe we can have some last questions before we finish today's panel. So you can do it while we are talking the last question. I would like to start again asking this question to Professor Aydinoğlu. And it's related with this. Again, it's not very scholar question, sorry about that, but I think it's interesting to discuss. We've been working in a workshop with the students about the earthquake during this is the second week. And we took a very holistic approach. We took a very broad approach. And one of the things we were talking is about what the people do when they are facing an earthquake. What happened, this situation when the people is in panic and they run. And so we were wondering, what is the right thing to do? Should the people leave the houses? Should the people leave the buildings quickly? Should the people stay? Let's say there are some guidelines saying that you should find this triangle of life, which is next to a furniture, strong furniture. Some people have heard or think that we should stay underneath beams. So to my knowledge, I come from Chile, which is also a seismic country. And what we are advised there is not to leave until the shake is gone. And then we should leave the building or the house. But again, Professor Aydinoğlu, what is your opinion on this regard? Or what do you know about this? What we should do in the case of when the earthquake happens? What should be our actions?
Normally, and ordinary people, of course, have practically no idea of what structural system his or her building has. So, there are old beliefs, for example, now that stay underneath the beam or the door entrance and something like that. These are the old stories that we heard from our childhood. Okay, but now they are all irrelevant. There are several different systems. So all I can say as a general, so to say, rule is to find a table or something like that that would cover your head and go under it, you know. So, or if you don't have such a thing around you during the earthquake, you just, you know, sits down on the floor and they try to save your head, you know, by any means that you can do during that. But in no way you should try to escape until the shock or shaking ceases. So the best thing is to find a place that could save your head, especially from being damaged or hurt. The ideal way is to go under a table or something like similar, or under a bed or whatever you might find in that rush. There is no, you know, general guidance about that. Yes.
But this is very interesting to hear your opinion. And Professor Charlson, what do you think?
Well, I largely agree with Professor Aydınoğlu. However, I'd just like to say this, that if you go under a table, that means that you are protecting yourself against falling objects that are quite light, like a suspended ceiling or a light roof. But if you're in a multi-story concrete building, table will be totally crushed and you would be killed. And so if you're in a heavy concrete building, I would agree that it's better not to move during the shaking. You mustn't try and leave the building. But I personally would try and find a triangle of life. I would lie against something that the floor slab couldn't crush, like say some very strong cupboards, or a very strong piece of furniture, but I wouldn't actually lie underneath it. But I agree with the principle, you know, don't try and escape a multi-story building, because it's very likely the stairs will get damaged and could collapse. And I mean, it's very likely, you know, the infill walls will collapse. And so that's where a table or a triangle of life, you know, could really save your life in that condition. But I mean, it depends on the type of construction of a building. I can remember some years ago, there was a damaging earthquake in Pakistan. And a teacher was just about to go into a classroom when the earthquake struck. And instantly, the classroom collapsed. And I mean, it was just instant. You know, nobody could even move before everybody was killed. But the teacher was just fortunate he hadn't entered the building. But I mean, the only way that the children would have been saved is if they could have found triangles of life, you know, inside their heavy building.
Well, that's a very tragic story, what you just said there, but I understand your point. Okay. Well, we have come to the end. I don't see any questions in the chat, so if someone would like to ask. But in the meantime, I would like to give again the stage to both our guests. If you would like to remark or to highlight something about your presentation or something you would like to say before we close the session? Professor Adinolu?
I may show a additional slide, if I may, regarding the, okay. Can I share the screen? Okay.
You can do that, yes.
Excuse me. Well, there are some essential requirements in our seismic code for the preferred structural system arrangement in seismic design. And some of them actually are directly related to architectural design and architectural alignment. These are exactly almost same or similar to what Professor Charlson already mentioned. But these are listed in an annex in our code, and a similar annex or similar chapter, I remember, is also present in Eurocode 8, European Seismic Code. So first of all, these are the six general principles: simplicity, regularity in plan, for example, symmetry and elevation in the Southwick stories, as already mentioned. Redundancy, this is another topic which requires maybe more time to discuss, but this is one of the essential requirements. Sufficient stiffness and strength, sufficient ductility, and sufficient diaphragm stiffness and strength. Especially in transverse diaphragms, this last item, which has already been mentioned by Professor Charlson, is quite important and generally ignored in most cases, unfortunately. And especially in modern architectural, there are sometimes we have large atriums and large holes in slabs without taking any precaution, to transfer the seismic loads from one element to the other, and they provide the integrity of the structure. So these are the, of course, in our seismic code, the readers can read this annex in chapter 4. In chapter 3 of the code regarding these principal requirements. Thank you very much.
Thank you very much, Professor Adinolu. Professor Charlson, would you like to share with us your last remarks?
Well, I think I would just like to encourage all architects participating to try and revisit their current design project and just see if you're satisfying the principles that we've talked about. I mean, both of us presenters have given a lot of principles tonight, and it would be really good for you to look at your designs and just see what changes might be necessary so that your designs, can be considered earthquake safe. I mean, I'm surprised that the students haven't got many questions, because in order to achieve the 7 principles I've given you, it's quite difficult at times. And you're going to have to make some very careful compromises, and you're going to have to integrate your structure really very carefully with your planning. And so it's not an easy matter to apply these principles, but it can be done. And I really encourage you to try and adopt them and apply them in your design projects. And in that way, you'll be preparing yourself, for a very good professional career. So thank you very much.
Thank you very much, Andrew. I have 3 questions. If I think we still have some time, I would like to share the questions with you. So first is a comment and questions. It says, it's from Meltem, our dean. He says, thank you very much for the insightful presentations. I have a question. I think this question is mostly for you, Professor Adinolu. I have a question about the factor of foundations and soil conditions into damage. In case of bionuclear liquid liquefaction, I think it means, is a problem. Nevertheless, high buildings did not get affected there. What are the changes in the codes in this regard? Will older buildings in the 70s or the 80s get affected because of foundation design, even if they were built in terms of columns and beams? Could you comment on that?
Yes. Of course, the soil issue and the effect of soil have been rather exaggerated in recent times, especially after the Izmir earthquake and Bayrakli case. Of course, as I mentioned, the primary effect of soil stiffness and strength is, first of all, is seen on the earthquake input. So these weak and soft soil deposits affect the seismic waves significantly. So therefore, that they should be considered. But this is related to the definition of the seismic input. And in seismic codes, now, especially in our last seismic code, as in other codes, we have a detailed section of soils and soil behavior and soil investigations and foundation design, a special chapter. So the soils are classified. There are standard classifications all over the world. And based on certain, investigations and tests and so forth, soil investigation is necessary, of course, especially if you don't have, firm soil. And in Turkey, these are, mandatory things to be done. And you specify what class of soil you have in your site. And accordingly, depending on the importance and size of the structures, you can either empirically modify the seismic input by using some coefficients, depending on those soil classes. So it means that you amplify or sometimes de-amplify the seismic accelerations, the seismic forces. Or in special cases where the soil is very weak or you have an important structures, then you may run analytical soil amplification studies, okay, in 1 or 2 dimensions. There are now very good software for them and so forth. So you can obtain the surface motion to be used for the design of your structure. This is one part. The second part is the foundation design, okay? Foundation design, and now I would like to mention that the people generally think that the earthquake damage occurs due to some failure of foundation here or there, rather than the high, inertia forces acting on the structure. So in Turkey especially, this is a general belief that the foundation should be very, very strong. Otherwise, the foundation will fail and therefore our building will collapse. they don't care or they don't aware of the importance and high magnitude of inertial forces or seismic forces. And therefore, it is obvious that in Turkey, foundations are generally designed and built very conservative. For example, mat foundations are everywhere in Turkey now, regardless of whether you have a good soil or bad soil. Okay. This comes from this, disbelief or wrong interpretations. Of course, you have to design your foundation like you design your foundation for non-seismic effects. You have to consider the seismic forces and design your structure foundation. Now, of course, especially in big cities, now we are being forced to construct our buildings on weak soil conditions, inevitably because of lack of land. So, for example, in recent years, we are using more and more deep foundations, mainly piled foundations, okay? Now, for piled foundations, our new code, for example, has a very much detailed requirements because that they are being used more and more frequently because of the reasons that I mentioned. For example, in Bayraklı region, if you want to make a new structure, most likely you will have, you would need to have a piled foundation. And actually there are some piled foundations, but I doubt whether they have been designed properly, considering the proper seismic effects. But our new code, fortunately, contains all of them in great detail, in sufficient detail. Now, one of the important points that discussed and talked about very, very much, almost after especially after the earthquakes, is the liquefaction phenomenon. Liquefaction occurs in a sandy, silty soils. If you are building your structure on a former river bed or something like that, of course, you are bound to face such a problem. First of all, this is a matter of city planning issue. I mean, the city, the municipalities or the government shouldn't allow, the construction to be applied on such adverse soil conditions prone to liquefaction. This is important because liquefaction is a very bad thing. It can be, prevented by some measures, but generally you should avoid by planning constructing buildings on such conditions. Well, in our codes, again, in the general practice now, there are practical methods to identify the liquefaction potential of any site. So there are various levels of methods, simple to complex, and there are experts, and in our code, these are detailed in satisfactory manner. So whether a site has a liquefaction potential can be determined relatively easily by following those rules. And you should avoid, of course, making construction unless you are forced to do. And if you are forced to make a construction, and there are some soil improvement methods, they are also improving in recent years. You have to, but it's a matter of expertise, of course. And you have to apply geotechnical experts. There is a field of earthquake engineering now. It's called geotechnical earthquake engineering. You have to apply those experts to find the solutions. But in general, so in short, I should say that this matter is generally being exaggerated by mainly, non-civil engineering people dealing with the geology and geophysics and so forth in Turkey. It's an important matter, but not as much as discussed in the media.
I think that was very clear answer, Professor. Thank you very much. I have another question. Well, the third one was a comment. So the other question I would like to ask Professor Charlson is a bit general, but I think you are the right person to address this one. He says, I would love to know about resonance during the earthquake. How can we protect our design against resonance?
Okay, well, the main way we prevent resonance being a problem in a building is by following the earthquake code of our country. Because every building has some resonance. We can't avoid some resonance. But the worst resonance occurs when the natural vibration of a building is similar to the vibration of the soil underneath the building. And so in the recent earthquake in Izmir, most of the buildings that got damaged, they were built on soft soil, which was like building on a jelly, because during an earthquake, the soft soil resonates itself like this. And then if you put a building on top of the soft soil, the building will resonate again or more than the soil underneath it. And so resonance is particularly bad where you have the natural vibration of the soil being similar to the natural vibration of the building. But anyway, the codes that engineers use do take that into account. And so if you are designing a building on soft soils, the building has to be stronger and stiffer than if it were built on rock. And so engineers are aware of the resonance effect, and it is largely accounted for in the strength of their designs. But maybe, Professor, would you like to add to my comment on that?
Thank you. Well, you're right. Resonance is everywhere, of course, because there is a natural period, natural vibration characteristics of the building and that of the soil response. So, but the people think that resonance is the main thing, and if resonance occurs, the building collapses. Otherwise, building doesn't collapse. This is not that simple. I'm sorry. Well, as Professor Charlson just mentioned, for example, I already showed the response spectra, okay? The response spectra shows the effect of seismic effect, okay, within a given period range, okay? In a given period range, seismic effects are higher. For example, in Bayraklı area, we see clearly from the response spectrum that in between 0.4 and 1.5 seconds, the waves are amplified, okay? So if you have a structure coinciding or near to these frequencies or periods, you will have a higher effect. That's for sure. And our response spectra specified in the codes also reflects the effect of soil, as I mentioned, by some modification factors. And the shape of the response spectrum is also controlled by soil to a certain extent. And if your structure's natural periods or governing natural periods are coinciding between in those periods or near to the, and it means that you will have higher seismic forces acting on your system. So it's automatically being considered. So, of course, there are some extreme things that, you know, leads the people, you know, thinking that this is an abrupt thing. It occurs or not occurs. It's a very interesting example. For example, in the city, Mexico City, you know, lies on a very deep alluvial soil. And if you know, there are earthquake occurs at every 20 years or so. I remember, for example, in my professional life, the one in 1966 and 1965. I'm sorry, 1985. So if you, especially in 1985, of course, we have a lot of instrumentations obtained and records obtained. So we have almost a sinusoidal surface motion on the surface with a dominant period of around 2 seconds. So in that building, in that earthquake, the high buildings, relatively with predominant periods near to 2 seconds or so, have been affected quite intensively. Okay, that's a more or less clear resonance, but the soil conditions there is a very unique one. You know, you cannot find such a unique situation almost nowhere in the world. I haven't seen anything like that, like Mexico City. So these are very special instances. Okay, but in general, okay, Professor Charlison very rightly says, okay, the resonance is everywhere. Okay, resonance is a natural phenomenon, dynamic phenomenon. Okay, but we are considering it. Maybe not explicitly, but implicitly considering it in our design. No problem.
All right. Thank you very much for your questions. I think we are running out of time. So I would like to read a comment from the head of the Department of Architecture. She's saying, thank you very much for these highly informative presentations, discussion, and comments. I'm pretty sure that they will be so helpful for our students in their design processes. And I would like to personally join to that. Congratulations and thanks. I would like to finalize here by thanking our two very, very distinguished guests. I want to say that I have enjoyed today both presentations, and I'm also very, very sure that they have helped to reinforce the idea that the architects should be aware of their designs and the influence of their designs in seismic designs. So, Professor Aydinoğlu, thank you very much for your contributions today. Thank you very much for joining us.
Thank you.
Professor Carson, again, very nice to see you. Thank you very much for joining us.
You're very welcome.
Thank you very much, and thanks all the people from the audience to attend today, and the people who made this possible. I mean, logistically wise speaking, thank you very much. And I guess there are some questions coming. I will send it to you by email, so maybe you can address this later, and we can provide these answers because they are coming now. All right. So again, thank you very much to everyone, and I hope to see you around soon. Thank you very much, and
bye.
Thank you.
Goodbye.